rational functions, right? And you are supposed to know by now what we mean when we say rational, right? What's a rational number? It can be written as a fraction, right? So when you say rational function, it means this is a kind of a function that can be written as a fraction. And that's why it's difficult, because for the most part, we're not really very good with fractions when they don't involve variables. Now you throw variables in there, it gets harder, right? So that's why this chapter ends up being the hard one. You know, we're going to do two things with it today. Remember, there's three entities that we study here in math, right? First, we learn how to simplify expressions. We learn how to solve equations. We learn how to graph functions. We're going to do the graphing functions part first. So that's what the first couple bullets are. And then after that, we're going to learn about the graphs, some particulars about the graphs of rational functions. Let's go. So rational functions are functions that can be written as fractions. Generally, we will write a rational function as a polynomial in the numerator divided by a polynomial in the denominator. Okay, and the standard is to say p of x is the numerator, q of x is the denominator. Although in some books they say n of x for numerator and d of x for denominator. Okay, doesn't matter. Why would it say at the end here q of x does not equal 0? Can't divide by 0, right? So that is one of the particulars about rational functions. You've got to make sure you're not dividing by 0. And so if you've got a polynomial in the denominator, if it has any zeros, that's going to be an issue. Okay. So the graphs of rational functions, except for one case, are not one standard shape. They're not one standard shape and then you move it around by adding and subtracting and all the things that we've done with all the other functions. However, there is one that does work that way. And that function is called inverse variation. Okay? An inverse variation has the form y equals k over x. And again, x does not equal 0. K is a constant. It's not a variable. It's taking the place of it. It could be 2 over x. It could be 4 over x, right? It's some number divided by x. That's what an inverse variation is. And the reason why we call it inverse variation is because if I take this first one, y equals 2 over x, what will happen to the value of y if the value of x increases? If x increases, y has to decrease. If x decreases, y has to increase. They are going to vary inversely, right? As one goes up, the other one goes down. That's what you mean by inverse variation. I mean, we actually did in chapter 2, which is about linear, we did direct variation. Direct variation was y equals kx. So they're both at the same level. When one gets bigger, the other gets bigger, right? But for this one, it doesn't work that way. Now, we're going to graph using a transformational approach, right? By adding, subtracting, and putting minus signs and all that good stuff. But when you look at these things, don't look at the numerator of 2 or the numerator of 4 and think like, oh, that's a stretch. That's not a stretch. That's part of the parent function. Now, what I've graphed over here is the y equals the thin line, which is a little bit inside. Y is a little bit darker line, and a little bit out, and a little bit out. The main thing to point out there is they're not much different. They're not much different. Changing what's in the numerator there won't change. We are sketching. It's still 2 or 4 or 6, whatever. It's still going to be one will be in quadrant 1, and one piece of quadrant 3. So the main point to get out of this, the 2 and the 4, those are right. They are part of the parent function, and they don't function, and they don't in any important way for us. Hope I didn't. looks good. Of standard graph then of an inverse. Now, there's going to be, as you can already on here, something that we learned about logarithms, and those are asymptotes. X does not equal 0. Okay. Well, if x does not, that means the y-axis, this y-axis, that makes the y-axis an asymptote. Equation for that is x equals 0. So 0. So the graph will never touch that line. It'll serve, but it'll never touch, which means it has to either positive infinity or it has to veer infinity, right? And it'll just get infinitely close. Right? You know about fractions. If a fraction equals, it's because the numerator equals 0, right? 0, right? 0. There's no other way for a fraction. So since this fraction does not, y is never going to equal 0. Again, for x, that would make y equal 0. It's kind of like what we said with exponentials. Means there's not to make that graph actually touch the x-axis, they're asymptote, right? Two in the same graph. So the logarithms, which each one had 1, right? 1, right? We'll say horizontal, y equals 0, x equals 0 on the same background, and that's right. And first quadrant and third quadrant, these are, let me see if I'm here. And those are called brackets. Branch. What would be 0, right? Because that's the one value that x can't, but it just can't be that. So you would say the domain x does not equal 0. Give it a range. Y does not equal 0. Okay. It's the way the the book asks range with these problems. What we're really supposed to know. Some of these graphs kind of crazy for actually range, but domain is important. All right. So what would you expect if I started with this parent function of 2 and put a minus in front? What does that usually do? It flips it across the x-axis, right? So in branch in the first quadrant, you got a branch in the fourth quadrant. Branch in the third quadrant, you got it in the second quadrant. Other than to change the asymptotes, so it didn't change the domain or the range. That's it. It just means you would sketch your branches. For. I'll go write that in. Flip across x-axis. Now, doesn't that kind of look like a flip across the y-axis too? Is there really any difference? We don't deal a lot with flips across. The way, if you have a function equals f of x, okay, the way you make it flip across the x-axis is you put a minus here, right? The way you make it flip across the y-axis here. Okay, for our much difference whether I put that minus in in front or whether I put it just in front of the x, it's still the same x. It's still the same x. So it is the same, whether or not I the x or flipped it across the y. But generally, minus in front of a function flips it across the x-axis. Okay, what did it generally when we subtracted 3 inside? What's that? So notice this graph right here, the whole right 3. Okay, well which aspect? Is it the horizontal that it changed? It took and it moved it 3 over. Right, there's the new vertical asymptote. What about the horizontal asymptote? Did that change? So that is here. So this is the line. This is domain of that. Shetty? X does not. Domain is x 3. I mean, it can equal anything else, but it can't touch 3. So x does not equal 3 is the domain. Okay. Due to the graph of a function, if you add a number up, right? So this is up 4. Okay, which asymptote does that move? It moves this horizontal line. So the new graph is going to look like, or the new asymptote there. Okay, did that change the vertical asymptote? Right, just taking this graph going up and down, doesn't vertical line still in the same place. So that. Okay. What is the horizontal asymptote? The equation for the line. I didn't ask for the domain. It said what is the y equals 4. The equals 4. The domain is domain. What value does x not equal? 0. It's 0. It's so it's the vertical asymptote. Vertical asymptote is the domain. So x equals 0 is the vertical asymptote. The vertical asymptote. X does not equal 0. Okay, so what is the graph of? Over x plus 1 minus 2. Left 1, 2. Okay. Of a the first thing you want to do is put the asymptotes in. If I'm shifting, this is left 1, but moved left 1, right? So first sketching the horizontal asymptote. Okay, so what is the equation? Y equals 2. Right, so now x equals -1. This is y. And then you look at this term there. It's positive, so you're going to sketch it in 1. Meaning, use these. Don't use the origin. Don't use these to be the center of the graph right there, of the graph right there, of the graph right there. Don't worry about plotting points. Just sketch. Just sketch. There's one, and there's right. What is the domain? Say again. Say again. X does not equal -1. Bothering us.
Share your number off your projector.
See the chair? Okay, so actually I was going to stop doing this, but in the fifth block regular algebra 2, they all you try things, right? So you know, for them, you guys are the higher algebra 2 class. You know, most of you guys, you do all your homework anyway. You got 100% for your homework credit anyways, and things, and get some more things thrown in that bin. That's it all. For them, most and being able to get credit for doing something, their homework grade from a 0 to a 50. So I mean, the whole point of this is you're participating in class. Do these on a page that you can hand in wherever it says that you try. It's on the table if you need it. Sketch the graph. Remember, you got to determine, then you got to draw your asymptotes. Sketch in the actual branches of the right. And what is this? Up. Okay. And then sketch in the asymptotes approach. So what is the vertical asymptote? That's the domain. For right. So the vertical asymptote right for, and then for the horizontal asymptote. 6, 2, 3, 4, 5, 6, 5, 6, 5, 6. So this is equals 6. X equals 4. And because it's positive, that like it's the origin, and sketch in 1, quadrant 3. pretty close to that. Domain. X does not. Okay, was I thinking of anything else? Let's try. What about if you have and you have to determine, well, what would be the equation for the graph? If the starting point is this parent function, then what shifts do you see in this graph? Notice that every grid line is 2. 2, 4, 4. Okay. Looks like that is 3 to the and this looks like it's how far? 4. Okay, so the question is, how do you make a shift of 3 to the left? And then you. So that's all in the denominator right there. I mean, the SOLs for this stuff, your equation, go to a graph, start with a graph, go to the graph, go to the asymptotes, go to the equation, any one of them do. So try to do the same thing on this one. Assume that you're starting with the parent equals 2 over x in the appropriate shifts. That is Gabriel. What did you have? X. What do you mean a shift right 1? Okay, and then what comes after? Minus 4? No. What is the domain? X does not equal 1. Put in a 1, you'd be dividing by 0. X 1. Transformational stuff we can only do with this rational function. And the truth is that when you look at it, doesn't actually have the form of a rational function. It is not numerator divided by a polynomial denominator. Considered to be that. I mean, you could make that into a rational function. By this term by x minus 1 over x minus 1, x minus 1 in the numerator and a polynomial in the denominator. Okay. That's what we take out of section 8.2, right? And then in 8.2, all the rest of the graphs of rational functions. And the graph, these are just three graphs of rational functions, and they are all quite different. There is not one standard graph for a rational, and so we don't spend any time all these odd shapes of graphs. That they're all characterized by asymptotes. You have vertical asymptotes, you have horizontal asymptotes, some asymptotes. All right. In fact, this one right here, that inverse variation, doesn't it? An asymptote here, it's got an asymptote here. So anyway, the point of this is the rational functions have irregular shapes, all characterized by asymptotes. So the SOL is actually vertical asymptotes. Find vertical asymptotes. The book actually does a little bit more. It also talks about something that's called a hole. So that's two examples from the previous slide. Both of these, the zero would be like, let's just say if it's what is the domain of this one right here? Since it's divided by x plus 2, you would say well, x does not equal negative. This one is divided by x minus 2. X does not equal 2. Both of those points are what you call points. The x values are points of discontinuity. Means that the graph I can't draw this graph straight line without picking up my pen. I'm going to have to get to a jump over an open hole and then start again. One, just like in inverse variations, I'm going to draw one branch, and I'm going to pick up my pen, and I'm going to draw the other. Points of discontinuity, and they come from of the denominator. But they look different because notice the similarity. Notice what's different in this one. Can you pick it out? What we're looking for? Tell what's in the first one that would change it. Like a vertical asymptote. Here's the key, right? There's a point of disk 2, which means there's a factor of x plus 2. X plus 2 in the numerator too. So cancels. So when your graph look like y equals x plus 3, and that's what this looks like. It's a straight line, y-intercepted line, but it still cannot have a value negative 2. Because then you'd be divided. That's why you've got to make a little open circle, negative 2, right? You go to x equals negative 2, go up to the graph, circle. That's called a hole. Looks like a. So points of discontinuity can actually holes or vertical asymptotes. A factor that is the source of the point of discontinuity factor in the numerator, it's a hole. If it doesn't, but in the end, for the zeros of the denominator. We're seen on the SOLs that they talk about holes, that are vertical asymptotes, and even in the pre-cal book, they holes. It's always just about vertical asymptotes. Okay, so finding a point of again. What did I just underline on the last slide? The zeros of the denominator. It's one thing if the denominator is already factored. Factor it. And I would say that's hard. A part of what makes this chapter hard. Besides add, subtract, multiply, and divide, fraction, variable expressions. It's also about factoring. And if you weren't good at factoring before, when actually the factor is embedded in a problem, something bigger than just that. Most of the time, relatively easy. They don't make it. Take that one as your factor. Come on, it should take you about 2.5 seconds. 2.5 seconds. Okay, so this is x plus 3 times x minus 1 times x minus, right? The factors of 3 that add up to negative 1 and negative 3. Okay, so now the points of discontinuity. X equals zeros of the denominator. 1 and The points of discontinuity are continuity, x equals 1 and x, right? Do either one of those factors here in the numerator? I mean, remember, the only way you could cancel, it's the whole thing is in the numerator and denominator. Take a 3 and cancel it. Factor of the numerator. It's a term. But canceling to be done here. So we would say the vertical asymptote x equals 1, 3. What is the domain? X does not equal 1, right? Now, when you are asked, you've got to include the x equals. 1 and 3, you'll get partial credit, but you're not getting all the credit. You know, I remember this is many years ago. In an Algebra 2 class, not in this classroom, and you know, describe which one of these is a horizontal. Half of the kids were doing this for the horizontal line. Literally half. Now, when there's only two, that's guessing. If the whole column, if you don't know, you need to know. So that's a vertical line. The way you name a horizontal equals. The way you name a vertical line is x equals. If you get it wrong, it matters. Writing the x and the y, you're not going to get all the credit because you got to show me that you know. Vertical asymptotes aren't. Okay. Denominator. Now, just because it's not factorable doesn't mean you couldn't try to solve it. What would I get if I tried to solve that denominator? X squared equals 0. Solve. Say what? Imaginary number. Which one? -1. Lee, you're disappointing me. If x squared equals negative, try to solve for x by taking the square root of both sides. Your equals plus or minus I. Right? Square root of -1 equals took the square root. You have to say plus or minus. We are looking for, you know, discontinuity on a graph, which only includes. So if you get an imaginary number like that, it means. So this one has no points of asymptotes, right? No of disk asymptotes or holes. Like that, right? Nothing wrong with that. You know, graph it. What will x squared plus 1 look like? Come on now. It's a parabola moved up 1. So it would look like that. What are the zeros? It never crosses the x-axis. It doesn't have any zeros, which is how to solve it. So C. Points of discontinuity. 4, right? I mean, there's only one factor. So you're going to say the point of discontinuity x equals 4. Okay? Is that or is it a whole? How do you know? How do you know? You have to factor the numerator and see, is a factor that cancels with that. Okay, how does that? Okay, how does that? Okay, how does it? Simple quadratic, how does it factor? How does it factor? Yeah. Yeah. So x plus 1 minus 4 divided by. So again, is that going to be a whole? Is that going to be a whole? Remember when it's a whole. So it has a. At x equals 4 Right. The graph would look like straight line, and it would have, you would go to x equals, make a little open circle. Okay, let's see. Which is a good one for? How about the first one? What are the vertical assholes? Too late. Remember, factor that in. That's just a pattern in the denominator in the first one. Difference of squares. Right. This is exactly what I was talking about back when we did all that. Difference of squares, which no math teacher can understand why, but when they put something like that in problems, in their mind, factoring problem ever. Right? It's a way of testing you on this rational stuff with, and we know factoring will be part of it, hard part of it. That's why you can't turn it in. You should see it immediately. 16. Oh, difference is 16. Oh, difference is y equals 1 over, Josh, x plus 4. So it's going to have pointed 4 and 4. Are they going to be holes or vertical? Numerator to cancel one of those? No. So it's a vertical. So you would say the vertical asymptotes are negative 4 x 4. What would you say about the second one? Like it. We did. Say again? X squared plus 3 is never going to equal 0, right? Right? I mean 3. Because x squared is positive, which is 3. So, I mean, it's not going to have any zeros. You know, this would be x plus 2, so it would have points of discontinuity at negative 2 and negative 1 would cancel the whole. But negative 2 is a vertical asymptote. See? X over x plus 2 times 2. So definitely there's 2 and x equals negative 1. Negative 1 cancels with the numerator. So you would say that's a hole. This is a vertical asymptote. They have vertical asymptotes at 4 and negative domain. Shadi? What? Not 4 and negative. X does 4. X does not equal negative 4. What? zeros to the denominator, all real numbers, right? That's right. X is not equal -1. That's it. That's it. That's dividing by zeros. That's how you determine domain. Okay, now horizontal asymptotes. Even though the ones we've seen so far, with exponentials and the inverse variation, fast lines that the graph was never going to touch. What a horizontal asymptote is. A horizontal asymptote is the value that y will as x gets large. It's graph trending towards when you go to the right end of the graph. Actually, it's like this. That let's say a horizontal asymptote on the it could look like the graph is doing this kind of thing. Right? At the horizontal asymptote, it looks like as x becomes large, reaching that line. See, in the positive direction. Now the truth is that when x was small, it crossed. The graph can cross a horizontal asymptote. Is small. That's okay. Vertical asymptote, never you can cross the vertical asymptote. You can. Right. Small, you say, okay, that's okay. But it should look like approaching the horizontal asymptote on either end. So we used a term for this when we were dealing with polynomials, and that was called the end behavior of the graph is what horizontal asymptote, whatever it is. Let's talk in terms of end behavior. Since some of you are coming from different classes, you may have spoken than we did, because every book deals didn't do this a couple of years ago, and in textbook or chapter 5, all it did was down and up, or up and down, or up and down, or up and down, and that was the whole thing, if you remember. But when it comes to horizontal asymptotes, end behavior. It means what's the graph doing at the edges, to the left. So the way you find horizontal asymptotes, very simple rules for it. The degree of the numerator and the degree of the denominator, by degree of a polynomial. It is the highest. Right? If you look at all the terms, and usually if you write it in standard, all the way on the left, whatever's that power, that's the power. Okay. So these are their rules. I think if you read them. I mean, these are not bad the way they're written. In the last version of the textbook, but maybe a little bit easier. Let's rational function. The polynomial in the numerator is a x to so that's the power, plus, and there are lesser power terms, but it doesn't matter. What we're doing here. In the denominator, bx to the n term plus which don't matter. Right. The a coefficients. The coefficients of the term. So the three rules are this. Sum, which is the degree of the numerator, is less than the horizontal asymptote. And that would be like inverse variation. Y equals 2 over, which has the highest power of x, the numerator or x. What's the power of x in the denominator? 1. What's the power of x in the numerator? That means it's x to the 0. So the numerator power than the denominator, which means it had y equals 0, the x-axis, which we already saw, right? That was it had right along the x-axis, okay? If higher power, a higher degree than the denominator, horizontal asymptote. I mean, that's like saying y equals x, right? You could call that, and that's the parabola goes up forever. It does not approach y. It goes to infinity on both sides, right? Which leaves the one last cases. Yeah, Karen. Okay. What if they're equal? What if they have the numerator and denominator? Well, then it's going to the ratio of the A over B. And that's what these are saying right here. I mean, B, y equals 0. There is none. So let's practice. Right? We can call it. This is rule 2. Yeah, I didn't like the way I did this, but okay. This one, y equals x squared over 5. Right? Which is the higher power, numerator or denominator? Numerator. Okay, what's the rule say? If it's higher than, what is the horizontal asymptote? It does not have one. Right? The degree of the numerator is greater than the degree. There is no horizontal asymptote. 2x over. They're equal degrees, right? They're both x to the first. Tell you would be the horizontal asymptote. The coefficients of the highest power terms, right? Oh, that was wrong. That's a 1. So what is the horizontal? Y equals 2 over 1. 2, right? 2, right? And then what about which is a higher degree? Numerator, denominator. What does the rule say? The horizontal asymptote is what? Y equals 0, right? 0 doesn't get you. Okay, you gotta say y equals. The highest power is there. Y equals. Right? Try, and then we're done. So look at those 3. You could just write it down to yourself. Which one? Y equals 0. Which one has none? One has none. The other one. So which one does not have? C, right? Right. Which one has? Okay. Okay, denominator, y equals 0, equals 0. Okay, what is the horizontal asymptote of the last one? Right? Because they have equal degrees of the coefficients of the highest degree terms. Y equals negative 2 over 1, 2 over 1, 2 over 1 is 2. Typical kind of a mistake that we make, and it's like this, but it could be something like this, equals 5 plus x divided by 1. What is the horizontal? Come on, Lee. Yeah. It'd be y. It's the coefficients of the highest degree terms. Written on the left, it's still the highest degree term. It will say it's y equals 5. But that wouldn't be right. Degree terms in the numerator and denominator. It's very convenient when everything's always written. Doesn't have to be. And sometimes it's not. It doesn't count to say you were going to. So that's what we did. We learned about inverse variation, which was a particular function, and actually transformed it, and putting minus signs in and all that good stuff. About discontinuous domains of the rest of the rational horizontal and vertical asymptotes. Describe the end behavior. That's the homework.